Assalamualaikum and hi to all. So this is part 7 for chapter 1 of Exergy. So in this video, I'm going to explain subsection 7, Exergy balance, closed and open system. Exergy balance, closed and open systems. Exergy balance general. So we already discussed in the previous video how to derive the Exergy balance equation and how do we derive the Exergy from each heat energy source. So here we are looking into the general equation of the Exergy balance equation. So the general equation is Exergy in minus Exergy out minus Exergy destroyed equal to delta X system or Exergy change of the system. Okay, so here we look the delta X system is the change in Exergy, which is a change of Exergy in the system, and X in minus X out is energy coming from the net energy to Exergy transfer from heat, work, and mass. And then we have Exergy destroyed, which is coming from the Exergy destruction. So we can further expand this equation to be something like this. So X heat in minus X heat out, which is the net Exergy transfer from heat, and in a bracket X work in minus X work out is the net Exergy transfer from work, and X mass in minus X mass out is the net mass transfer and net Exergy transfer from mass minus the Exergy destroyed is equal to the change of the Exergy. So as I already mentioned, the one which are highlighted in the pink color is the net Exergy transfer from heat, work, and mass. And then the one which are highlighted with green color is the Exergy destruction, and the blue color is the change in the Exergy. So X heat in minus X heat out, the equation is as shown in this slide with X heat equal to in the bracket 1 minus T naught divided by T times Q. And for the work which is coming from the boundary work and also from the mechanical work, which is shown as in this figure, and then from mass, X mass equal to XF, which is coming from the inlet and outlet of the mass flow in a control volume. Then we know the Exergy destroyed, where it is calculated based on the entropy generated as shown in this equation. Exergy destroyed equal to T naught time entropy generated. And then this is the Exergy change in the system. Change in the Exergy. So delta X system equal to delta XF for control volume system or open system, and delta X and F for closed system for a closed system. So for Exergy also, we also can use Exergy. We can change the equation of Exergy in terms of flow rate by dividing it into the based on time taken. So if the system is steady or the Exergy analysis of engineering device is steady, so the Exergy change of the system is equal to 0 as shown in this slide. Reversible work, WREV. So let's say we have an control volume system which has a mass flow rate in and mass flow rate out. We have a Q heat supplied to the system, and the heat generate work to the turbine. So in this case, for reversible work, for reversible system, the work done to the system is equal to the reversible work. And the Exergy destroyed, for this case, since the system is reversible, there is no Exergy destroyed, so it will be equal to 0. And in the case of a steady flow system, for this case, it is the steady flow system, the rate of Exergy change of the system is equal to 0. So from the Exergy balance equation, which is the general equation, we have net Exergy transfer from heat, net Exergy transfer from work, and also net Exergy transfer from mass flow in and out minus the Exergy destroyed. It is equal to the Exergy change of the system. For this case, we have dot, meaning that it is divided by delta T. So for the case of the system which I show on your left hand side, there is no work in from to the system, and there is also no heat out from the system. And for this case, the system is steady flow system, so the rate of exergy change of the system also will be equal to 0. And since this system is reversible, the exergy destroyed also will be equal to 0. So after we remove all these equations which are not related, the exergy work out is equal to the work reversible out, equal to the rate of exergy in from heat plus the rate of Exergy from mass flow rate in minus Exergy from mass flow rate out. So this is the reversible work for open system and steady flow. So, and then we look into the adiabatic system. So for the case of adiabatic system, we completely insulate the system. So there is no heat in and out of the system for this case. So looking back into the work reversible out, which is equal to x dot heat in plus x dot mass in minus x dot mass out. So for the adiabatic system, the heat will be equal to 0 and the work reversible out will be equal to the mass flow rate in, Exergy from the mass flow rate in minus Exergy from the mass flow rate out. Additional second law efficiency equations. So we have the general definition for second law efficiency, which is equal to Exergy recovered divided by Exergy expended for work producing device, and also another equation is 1 minus Exergy destroyed divided by Exergy expended for work consuming device. So it is also equal to the thermal efficiency of the system divided by thermal efficiency, reversible thermal efficiency of the system. So for steady flow devices, which is adiabatic turbine, the second law efficiency is equal to work out divided by Exergy at state 1 minus Exergy at state 2. You also can calculate the second law efficiency of the turbine by using this equation, which is based from the enthalpy at state 1 minus state 2, enthalpy at state 2 divided by Exergy at state 1 minus Exergy at state 2. And we also can use the work out divided by work reversible out. And the last one, we can use 1 minus T naught times the generated entropy divided by Exergy at state 1 minus Exergy at state 2. Now we look into the adiabatic compressor, which is the work consuming device. So the second law efficiency is equal to the Exergy at state 2 minus Exergy at state 1 divided by work in. And then we also can use the enthalpy equation, which is equal to Exergy at state 2 minus Exergy at state 1 divided by enthalpy at state 2 minus enthalpy at state 1. And we also can use the work reversible in divided by work in. And the final one, we can use the 1 minus T naught time entropy generated divided by H2, which is the enthalpy at state 2 minus enthalpy at state 1. Please look carefully this equation, and please identify carefully which one is the work producing device and which one is the work consuming device, and carefully select the proper equation you need to use in your calculation. Revision questions for Exergy. So for your further understanding on the topics of Exergy, please try to do all the question which are stated in this slide. And this question is from the Chengel book, Thermodynamics and Engineering Approach, 7 editions. This is the end of part 7 for chapter 1, and this is also the end of chapter 1. Hopefully you find it useful for your study, and thank you for your attention.